Hello, we are Team 103. Here's our project checkpoint number 3, and here's what we've been working on.
Due to the current feedback from our stakeholders, this is our current concept design. Basically, the goal of this was to balance a sheet on top of 4 of our folding legs.
The team's goal is to include curvature robotics into our product by having claws and servo motors change the angles of the table legs for guests at the museum to be able to interact and be able to see a clear visual difference between different angles in the legs.
What you would do is you'd stick your hand closer or farther away from the IR sensor, and based on that, it would curve our legs of the table to make the top balance. So essentially, you're just trying to make the entire table balance. The goal was to incorporate Bluetooth via the phones of the patrons at the Fleet Museum so that they could check the curvature of each piece as they were interacting with the exhibit.
Currently, our product design includes a PCB, which is shown in an orange box shape, along with being powered by a 9-volt battery, including the PSOC BLE module, a diagnostic LED, a voltage regulator, a speaker, distance sensor, and tripwire sensor, in order to make our exhibit exceptional.
For our non-project required subsystems, we did 4 servo motors, each connected to the PSOC, and an LED and potentiometer debug tool also connected to the PSOC.
From the schematic, we created a PCB layout for the entire design. We took each component and created or gathered together their own individual footprint and then created traces in order to have a completely successful PCB and have it manufactured in Peralta.
Okay, here's our schematic that details each subsystem and how it connects together. However, we each worked on our own subsystem.
For our voltage regulator, we selected the LM317BT. That's going to be our main component for this subsystem. We have a 9-volt battery that's going into the voltage regulator. The voltage regulator circuit is followed thereafter, and then after that 220 ohm resistor, R6, we have 5 volts running throughout the rest of the system, as well as the other 3 subsystems.
For our distance sensor, we used a UART component that had both an emitter and a collector in order to measure distance. That was then connected to an op-amp to better read the signal.
So for the tripwire sensor, we used the QSE159 photodetector and the QEE113 emitter. And so basically it's running through a bypass capacitor, power runs out to our emitter, and then we have the tripwire sensor that detects a certain wavelength of IR light. It sends it through the op-amp, it boosts the signal, and then it goes into the PSOC, which reads it and outputs it to the speaker.
For the speaker part of the project, a PWM signal is sent through a resistor and a LM386 power op-amp, and then through a 220 microfarad capacitor to the speaker to help reduce any static and emit the clearest sound possible.
For the software, we started with our initialized system. So basically it checks our libraries, it starts all of our sensors, our ADC and our UARTs. So in our main loop, it initiates, it reads input from the sensors, it updates the state of the device, and then sets the physical outputs. And those are just our read and writes essentially. And then as far as the tripwire sensor goes, it inputs from the PSOC, has an ADC signal. It reads a value, and if it's greater than a certain value, like a constant, then the PSOC knows that it's tripped, and it sends a signal out to the speaker, which then plays a sound. So basically for the IR distance sensor, what it's doing is it has set values for each different function of the eye sensor. So if your hand is farther away, it's outputting a different value, which then either turns the motor clockwise or counterclockwise. If your hand stays in the same place, then the servo remains unchanged.